In this question, we're given a filter with a spectrum or frequency domain representation given by two unit step functions. And the question is, what kind of filter is that? So let's look at what that looks like in the frequency domain. So let's try to plot that. Whenever you have a unit step function, you're interested in when the step actually happens. So looking at that, we can say omega equals minus omega naught. And for the second one, we can do the same and say omega equals omega naught. So we have a reflected unit step function. I say it's reflected because of that minus sign that happens at omega equals minus omega naught. So if that's minus omega naught, and that's omega naught, and the axis is frequency, then my reflected unit step will look something like that. So if I were to do it in another color, it would look like, it would look like that. And then at omega naught, we have a positive unit step. So that's the plus sign there. It's not reflected because we have a positive omega. So it goes up again, same amplitude, and continues. So this is the spectrum of my filter. So it's symmetric on the frequency axis. So to determine what kind of a filter it is, look at one side of the frequency axis. And you see that low frequencies are blocked, high frequencies are passed. So I can say, this is my pass band that extends to infinity, and this is the block band. So these frequencies are all blocked. So what kind of a filter allows high frequencies to pass and blocks low frequencies? So we call that a high pass filter. So remember, this is the frequency domain representation of a high pass filter. And we used our elementary functions, which we often associate with the time domain, but they're equally applicable in the frequency domain. So that's how you'd answer a question like that.